Hello everybody, this is Mika Seppälä. In this video I discuss a method to compute volumes of certain solids by slicing the solids in a suitable way. This is very effective in many situations. Consider the solid of revolution obtained by letting the domain under the graph of a function f rotate around the x-axis. This solid of revolution is shown here on the right. The volume formula was obtained so that we first approximated the domain under the graph of the function f by rectangles corresponding to a Riemann sum of this function f. And then these rectangles rotate around the x-axis. Each rectangle forms a cylinder, and the union of these cylinders is an approximation for the solid of revolution. The union of the cylinders is shown on the left and the solid of revolution on the right. And that observation led to the volume formula. The volume of this solid of revolution is integral from a to b pi times f of x squared dx. Now consider the same solid of revolution and slice it with a plane perpendicular to the x-axis, intersecting the x-axis at the point x. Now such a slice is a disk of radius f of x by the definition of this solid of revolution. And the area of such a slice is pi times f of x squared. So in this formula for the volume of the solid of revolution, we integrate from a to b pi times f of x squared dx, that is, we integrate from a to b the area of the slice. And this can be generalized. Whenever one has to compute the volume of a solid of revolution or more general type of a solid, one can intersect it with planes perpendicular to a certain line. If this line is the x-axis, then one integrates with respect to x from a to b of the area of this slice. So the volume is also integral from a to b, area of the slice, corresponding to the intersection point x dx. So integral from a to b, a sub x dx. This is a useful way to compute volumes of certain solids. Consider a solid that looks a little bit like a hat. The bottom face of this hat is a disk of radius 1 with center at the origin, and every cross-section perpendicular to the x-axis is a square. In order to compute the volume of this hat, we slice the hat with planes perpendicular to the x-axis. Each slice is a square. If the plane intersects the x-axis at the point x, then, since the bottom face is a disk of radius 1, it follows that each square is of side length 2 times square root 1 minus x squared. And therefore the area of each slice is side length squared, that is 4 times 1 minus x squared. This is the area of a slice, and in order to get the volume, we integrate this area. So the volume of this hat is now the integral from -1 to 1 a of x dx, where a of x is the area of a slice perpendicular to the x-axis, and the limits of the integration -1 and 1 come from the fact that the bottom face of the solid is a disk of radius 1, therefore x varies between -1 and 1. And now this is integral from -1 to 1, 4 times 1 minus x squared dx. This 4 times 1 minus x squared is the area of a slice when the solid has been sliced with a plane perpendicular to the x-axis, intersecting the x-axis at the point x. This function 4 times 1 minus x squared is easy to integrate. An antiderivative is 4 times x minus 4 over 3 x cubed, and we substitute to this from -1 to 1, and we get the answer that the volume of this hat is 16 over 3 volume units. So, as a summary, we have now observed that the volume of a solid of revolution, or more general solid, can be computed by slicing this solid by planes perpendicular to the x-axis and integrating from a to b the area of such a slice, AX. This slicing can be done in a more general situation. One may also slice with planes perpendicular to any given straight line, but then one must integrate with respect to a point or variable that indicates a point on that particular straight line. Now, if the straight line is the x-axis, then the integration is with respect to x. So the volume of this solid is integral from a to b, area of a slice, dx. Very useful formula.